We'll be talking about our discovery of superconductivity in cobalt. And this is the first time I'm giving this talk in India. Last week I had given it in China in Fudan University. So, let's see. After a brief introduction, I'll just first part of the talk would be loss of ferromagnetism, how we found out in cobalt. The second part is the emergence of superconductivity. Here we'll see that in non-magnetic cobalt, you can see superconductivity, experiments to the point contact experiments and the 4 probe. And finally, I'll show some part of the theory, how it explains the transition temperature. So cobalt has been very fascinating for years, I would say centuries. So from bulk cobalt, lots of measurements have been done, lots of experience we gathered. But going dimensionally lower, also there has been many interesting studies. 2-dimensional layers, monolayers of cobalt. Then 1-dimensional chains, basically atomic chains. You add just one atom after another, you build up a long atomic chain. There had been fascinating experiment results in 1-dimensional chains, but then 0-dimensional single cobalt atoms. And this has also shown very fascinating results. For example, the anisotropy of single cobalt atoms. This was about 9 millielectron volt, which is the largest, the strongest bulk ferromagnetic samarium cobalt. And compared to that, this anisotropy is about 5 times. So such interesting experiments have been done by going down in the dimensionality from bulk, which is 3-dimensional, to 2-dimension, 1-dimension, and 0-dimension. But still, there are a lot of things, a lot of fascinating stuff waiting for us. Is there other interest in this area? The geomagnetism, there is interest about that, because if you go to the core of the Earth, that is going from the crust to the core, this is how the pressure builds up as you go in depth. As the core is about 350 gigapascal is the energy, pressure. So you have materials like cobalt, iron, nickel, and their compounds in the Earth's core. How their magnetism is affected by pressure. Right? This was a question of importance in geomagnetism. So the question is, how do the magnetic materials, iron, nickel, cobalt, and their compounds behave under high pressure? That's why lots of high pressure experiments have been going on this kind of materials, like iron, nickel, and cobalt. So this is a theoretical prediction for cobalt under pressure. That means when you squeeze it down, pressurize it, its density increases. That means volume per atom decreases. When you do that, this is the normal density or the volume. Okay, sorry. So this is the normal density of cobalt. This is the atomic volume there, and this is your magnetic moment per atom. If you decrease the density, the moment goes up. If you increase the density, that means squeeze it further under high pressure, at about this volume or this density is about 1.4 times, the magnetic moment appear to be loss of magnetism. This has been a theoretical prediction. So low volume means higher density, and the pressure is needed to create this high density. So high pressure experiments people have carried out in order to see such a things. This is one of the high pressure experiments. Like this is a C and A lattice parameters, that means HCP, hexagonal close pack. So normal cobalt is hexagonal close pack structure, and it's ferromagnetic, that's we all know. But around 100 GPa, you have a transition to FCC, face-centered cubic structure. But from here to up to about 150, you have a mixed phase, hexagonal close packed as well as face-centered cubic. But beyond that, you have only a face-centered cubic phase. So here you expect loss of magnetism, but in these experiments there was no magnetic measurements. Yes, obviously it is difficult to carry out magnetic measurements under such high pressures. There are no magnetic measurements. Now, can there be an alternative to going under high pressure? So this is an example that I showed. If you have a polycrystalline thin film, if you have a polycrystalline thin film, there is a possibility that while you are growing the thin film by physical vapor deposition, the atoms can go into the grain boundaries, and they can create a pressure on the grains. And that is how you can have a higher density of the material. There has been some experiments done by these people, and they have shown. And through this mechanism, you can have a high density phase of a material there. So we have taken this path and the theoretical calculation there to explore these areas. So we explore high density non-magnetic phase of cobalt in a thin film. And this work is already published in February this year, this part. So we would have failed to discover this high density non-magnetic phase of cobalt if we had used standard experimental techniques for the measurement of density and magnetization. I'll tell you why. Because we found it in very thin layers. In the thin film, not everywhere. Major part of the film is still normal HCP cobalt. So any bulk measurements would give us information from that normal HCP cobalt. We wouldn't see any density enhancement. We wouldn't see any loss of magnetism. So we actually applied very depth-sensitive techniques. So from each depth, we can figure out what is the density and what is the magnetic moment there. And that is why we could find it out. So this is extra reflectivity and polarized Newton reflectivity. These are the experiments, main experiments that we carried out. So let me go into the experiments. So the structure of the film that we expect, sorry, I'm missing something here, some schematic were there. No, it's not here. So this is, we started with a film which is 25 nanometer grown on cobalt by electron beam deposition. So the structure that we expect is like silicon, cobalt, and when you take it out of the deposition chamber, you expose it to air, there could be an oxide layer, cobalt oxide at the top. It's a limiting oxide of about 2 nanometer. That's what you expect. Now, so if you probe by this technique, extra reflectivity or Newton, polarized Newton reflectivity, you would see only densities of these materials or magnetic behavior of these materials. But we find something different that I'll go into. But with extra reflectivity, what you determine is that you get a density averaged over the whole area of the sample. So if there is a distribution of density within the layer, you wouldn't see that. So over the whole layer, this averaged one. So if you take slices of, say, a few angstrom and go deeper and deeper, we see the average density over that layer. So just to see that like that, we just keep on probing different depths with the density information averaged over the whole area. So just to give you a brief introduction on the extra reflectivity, what you have for any material, for extra frequencies, the refractive index is less than 1. In optics, you know that for light, it is more than 1, right? But for extra frequencies, it's less than 1. So in that case, if your incident beam comes like that, it deviates away from the normal, just opposite to what you see in optics. So in that case, if you just reduce this angle of incidence, if you come at this angle, the reflected beam or the refracted beam would go along the surface. But if you decrease the angle here, then it reflects back into the medium. So this is called the total external reflection. So that means up to a critical angle of grazing angle of incidence, you get total reflection, and beyond that, the reflection falls, and it falls very drastically. But we get all the information from there. But this refractive index is written by this 1 minus delta. That's the real part. That's the refractive index. It takes care of the absorption part. And this delta is actually very small. It's of the order of 10 to the power minus 5 or 10 to the power minus 6. It's a very small deviation. But that is very important. That's what allows us to do many different things. So your experiment would be your incident X-rays. It would be detector here. You keep these two angles equal and keep on changing the angles. So then as a function of angle, you get the reflectivity. And this has a depth resolution which is very high depth resolution, about 1 angstrom depth resolution you can get. So the structure that we expect for this 25 nanometer cobalt film on silicon is something like this. But now we carry out the extra reflectivity experiments, and these are the results. These red points are the data, extra reflectivity data. Now if you have simple model, the cobalt oxide, cobalt, normal cobalt, and silicon, we know their density. You can calculate their electron density or the electron scattering length density. You can calculate the theoretical curve for the extra reflectivity. It should be like this, but you see it doesn't agree with the data. So now if you take this model, next one, an enhanced density at the interface between silicon and cobalt, then the fit improves. The chi-square value goes down. Fit improves, but it's still not yet so good. But if you take this model, enhanced density at the interface between cobalt and silicon, and near the top, just below the cobalt oxide layer, we get a very good fitting here with the chi-square values very small. So this is the structure that we get. Cobalt oxide, high density cobalt, normal cobalt, high density cobalt, and then the silicon substrate. This is the structure that we get. Now, if you look at this high density cobalt and the normal cobalt, this is the electron scattering length density, which is proportional to the density of the material. You see that ratio, take the ratio of these two, it's 1.36. So that means the density is enhanced by a factor of 1.36 compared to the normal cobalt. So we have such two layers which are high density. Now, let me put a question here. So this material is high density, we know. But is it high density cobalt or some other material which may have a high density, say gold? It may have high density. Although we know it is not there, but we put this to test in experiments. So I put a question mark whether it's high density cobalt or some other high Z materials over here. So we carried out Rutherford backscattering spectrometry experiment, which shows this cobalt signal here and silicon signal from the substrate. If there are any high Z materials were there, the signal would be on the higher energy side here. I show a simulation. If we had about 5 angstrom of gold, equivalent to 2 atomic layers, either on the top surface or anywhere distributed within the cobalt, even then our technique is so sensitive, rather for backscattering we'll see this signal clearly. But we see nothing here, so that rules out any possibility of any high Z materials over here. So this is now proven it is high density cobalt. Similarly, at the interface, you have a possibility of forming silicon dioxide, but silicon dioxide has a much lower density even compared to silicons. Of course, much less compared to silicon, so that is also ruled out. So these two layers are definitely high density cobalt layers. So once we have that, we'll go to the polarized neutron reflectivity measurements, which can give us the density as well as the magnetic moment density, which is very important for us. So here it's the same scenario. Refractive index is less than 1 for all material, but the refractive index formula is slightly different. Here is the nuclear moment part, and this is the magnetism coming from electronic system. So this is plus minus depending on the magnetic moment of the neutron. If your magnetic moment of the neutron is aligned with your magnetic moment of the sample, then you have one plus, the other one is, if they are opposite, then it's minus. So refractive index changes. Similarly, the critical angle also changes depending on the polarization of the neutron beam. So this is basically, you can tune your polarization of the neutron beam. It's called up or down. And you have apply a magnetic field, small magnetic field on the sample to polarize it in a particular direction. So these are the data for up spin and down spin. So the magnetic moment of the neutron parallel or anti-parallel to the magnetization of the sample. So these are the two sets of data, red for up spin and this for down spin. Look at this one, this fit. This is done assuming that silicon substrate, normal cobalt, and cobalt disilicide. If you assume that, we get a very bad fit. But if you have this model, high density cobalt here, high density cobalt over here, we get a very nice fit. So again, these results are consistent with what we found from extra reflectivity. Now this also has this is the density, it corresponds to this one. But moment density, magnetic moment density is this one. If we take a normal cobalt magnetic moment density, it doesn't satisfy, it doesn't fit. But if you take this moment density profile, that means moment going to 0 here and here, we get this very good fit. So now with these two experiments, we have established that we have high density non-magnetic layers, high density layers which are also non-magnetic. We have carried out many other experiments to cross-check these results. Now, the experiment that I showed earlier, that was carried out at the Bhabha Atomic Research Center, the Dhruva reactor, which the intensity of the neutron beam is very low. And if you notice that, we could carry out the experiments up to a momentum transfer of 0.04. Momentum transfer means basically your angle. So your incident angle and this reflected angle, if you increase this angle, you get more and more momentum transfer. That means this is wave vector out minus wave vector in, that gives you the momentum transfer. So we couldn't carry out the experiment to much larger value of this because the intensity falls, you see that almost nothing after that. So then we carried out the experiment, we repeated the experiment at the best neutron source. Where is this? Wait, how did it jump? The best neutron source available in the world is the Spallation neutron source at Oak Ridge National Lab, USA. Now here again you see that you need this, the magnetic moment density going to 0 and 0 here, and this is the actual density going up here and here. You have slightly different value of this because we have a large sample and we have just cut a little part of this and we sent there. So there is some variation, of course, lateral variation, but the major features are still the same. So now you see that we could carry out the measurements up to momentum transfer larger than 5 times what we could do at Bhabha Atomic Research Center, but still our results are same. Now we could also fit another parameter called the spin asymmetry. It is R up minus R down divided by R up plus R down. You see there's a very nice fit for this model. But if you take other models like uniform density and momentum of cobalt, they don't fit this. So all these results are consistent. So results from Bhabha Atomic Research Center, PNR at Dhruva, PNR at Oak Ridge National Lab, and these are theoretical results. Everything seems to be now consistent. Now the transmission electron microscopy, what we couldn't see, we got the average information over the whole area. But if we do transmission electron microscopy, we can see some more details. Here, this is plan view. That means we are looking from the top, and we can easily see that this is grainy and polycrystalline, as you see that. And there is a variation, density variation, this absorption contrast we have here. We just concentrate on one of them, so this dark one. And if we choose this area and take a fast Fourier transform, we get this. This is a FCC pattern, face-centered cubic pattern. That's what we have. Second, if we take a high-resolution picture of that, we see here the planar 111, planar spacing is 1.83 angstrom. Now, if you look at the grain boundary regions, this and this, 2 or 3, 2 means this grain boundary region, we see 1.83 within the grain, and at the grain boundary region is 2.06. That's about 11% contraction. The grain boundary regions are not dense. The atoms have gone there and they have compressed the grains. And if you look at this other grain boundary also, this one, you see this. This is lattice parameter. Here is 1.83, 2.06, but lattice planes are bent. That is to adapt different lattice constants. If you look at this one, you see the dislocations here. And this is a familiar situation for people who work in the epitaxial growth. If you grow one material with one lattice constant on a material which has a different lattice constant, you tend to get these dislocations at the interface. But here in the same plane, we see these dislocations, effect of different lattice parameters. So this 11% lattice contraction that we observe in this case. Now if we take the slice, we have a sample, we cut it vertically, look from the side. What do we see? So here from the top part, if you take FFT, you see FCC pattern. In the middle, if you take it that, you have ACP. So you know that we have ACP normal cobalt in the middle. That's what you see over here. And this is, of course, silicon, which is FCC. Now if you take the fluorescence yield going across this cobalt layer, this is what you see. The cobalt actually is slightly higher intensity here. Near the surface is higher intensity. That also corresponds to high cobalt. If you take FCC cobalt, FCC it's a copper, then they are symmetric, and we know that copper has no magnetism. So this situation has become similar to this situation. So 11% contraction of the FCC lattice that was taken there. Now, having established the presence of non-magnetic high-density layers, so we have the question, why didn't we see so far the magnetism, the superconductivity in iron, cobalt, nickel, anywhere in elemental materials where there is long-range magnetic order, like either ferromagnetic or antiferromagnetic, Cooper pair cannot be formed. So there is no superconductivity. But since we have got now a material, cobalt, which is non-magnetic, now we can expect that superconductivity may arise there. Okay? So with that, we just went forward. So this is the picture, periodic table of superconductivity. The blue ones, these materials, they are superconductor under ambient condition. And these green ones are those which are superconductor under pressure, when you apply pressure. Interestingly, from this iron, cobalt, and nickel, iron superconductivity is observed for the pressure range from 15 to 30 GPa with a transition temperature of about 2 Kelvin. But nickel and cobalt, no superconductivity has been observed so far. But let's explore. So our experiments were the point contact spectroscopy. In this case, you have a point contact with the sample, and then these are the details. You flow the current through this 1 and 3 and measure voltage through 2 and 4. And through that, we get these values. This is the resistance measurement as a function of temperature. You notice that at zero field, around 9.2 Kelvin, you have this drop in resistance. But it doesn't go to zero as a normal superconductor would, because you have the contact resistance there sitting. It's not just the pure superconducting material. Now, you notice that if you apply magnetic field, the superconducting transition temperature shifts towards lower temperature. It's a definite sign of superconductivity in resistance. And then what you have measured is the conductance as a function of voltage, applied voltage. And you see that near zero voltage, there's a huge conductance peak appearing there. To explain how it appears, I have a cartoon, but I put it below the whole talk, considering the time limitation. I'll talk about it later. So this is the feature that you see when you have a contact between a normal metal and a superconductor. You have this conductance peak over here, and if you apply magnetic field, the conductance peak reduces, and about 35 kilogauss, it goes flat. That means you don't have this conductance enhancement. That also tells you that now you have a contact between two normal metals. So you have gone above the superconducting transition temperature. So this is as a function of applied field. If you do the same thing as a function of temperature, this conductance peak goes to 0 at 9.5 Kelvin. Here the transition is 9.2 Kelvin. So you have gone just above the superconducting transition temperature. Now if you plot this AC, critical field versus temperature, and this is the expected parabolic curve that you see, but we notice that they don't exactly follow this. And this is not unexpected, because our material not a single material. It has different grains with different density distribution. In between the grains, we have normal metal. So you have a lot of complicated systems. So it doesn't fall on this, that we are not surprised about that. But similar results are also obtained with a copper tip and niobium, which is superconducting material. The similar features are obtained for that. Now this is, we take with another tip, palladium, which is also normal metal, just to verify or to confirm it. So this is again, we see the transition, superconducting transition. We see these features, conductance versus voltage as a function of field here. With temperature variation, we see this feature. Additionally, what we see, compared to the other one that I showed, we have two symmetric dips around this peak. And this is also a feature that can come for various conditions. Contact resistance, although contact materials, it depends on that. Also, it can happen because of Josephson tunneling. We have seen that the grains, superconducting grains, in between I don't have a superconducting material. So it is like a Josephson junction. So Josephson tunneling also can give you these dips. But what you can derive from this one, so this voltage divided by normal resistance, that gives you the critical current. So this is the critical current extracted from these plots. And similar results are obtained for silver and lead contact. Silver is normal metal, lead is superconducting, so they also showed similar results. But you notice that here we have a transition at 9.8 Kelvin. The earlier one I showed 9.2 Kelvin. Because when you make two contacts at two different places of the sample, also the contact sizes may be different depending on the pressure. So you expect, when you have a non-uniform sample, you can expect these variations. Now let's try the 4 probe measurements without the contact. The people would carry out in superconductivity such measurements. But let's see what we find. So here the connections that we got with silver paint, we didn't succeed. It came off at low temperature. So you had indium silver paint, and indium is a superconductor, we know. So first we tested it on a normal material. This is on a cobalt copper cobalt multilayer, which is not superconducting. And there we find a transition, superconducting transition about 3 K, and this is coming from indium. So we know that this feature we won't be able to avoid as long as you are using a contact material which is indium silver. So now for the sample, so this is at zero field. We have 2 transitions, 5.4 K. This is blown up here, and this is 3.7 K. 3.7 K is coming from indium. This 5.4 K is coming from our cobalt sample. And as you apply the increasing magnetic field, you see this transition temperature is shifting. Again, it's a definite indication of superconductivity. But you may ask that, again, that this is not going to 0. We can expect that because we have a structure, this cartoon shows we have high density non-magnetic grains which are superconductor, but in between you have material which are not superconductor, so you have extra resistance sitting there. Now you may ask a question, why is this 5.4 Kelvin here, and earlier one was 9.5 Kelvin about? So there, of course, when you do the contact measurements, there is some pressure that you cannot avoid. So that may be a pressure-induced enhancement in the other case of the TC. So this is also now available in archive. So now I explain the theoretical work that explains this TC. So this is again the spin-resolved calculations, and the dynamical matrix is in 5 minutes. 5 minutes, okay, okay. So that estimation of TC that is shown from here is, this is uses the Macmillan's formula. There are different parameters. This value is about 0.1 Coulomb pseudopotential. This electron phonon coupling constant is calculated. From here, this quantity is like the Debye frequency, and density of states at Fermi level that you can calculate, and then you plug in, you get these values. Now, 3.17 angstrom, as I mentioned, compared to this corresponds to 11% contraction, but uniform contraction from all directions. So if you do that, this I have already shown. This is non-magnetic, and this is the phonon dispersion, and this is the green one is the phonon density of states, and the red one is called the Eliasberg spectral function that is used in the calculation. So if you do all this, what you find, your TC is about 0.3 Kelvin. But this is FCC, just a uniform contraction. But in a thin film, you never expect a uniform contraction. You expect anisotropic contraction, or so you introduced a strain in the calculation. That means the FCC lattice, this is the top, and this is the halfway positions. And if you define a unit cell by this way, it's a tetragonal, and then you apply strain along this and this, then I'm not going through all of them. The last one I say. So this is 6% expansion along this, 6% expansion along this, and 12% contraction along the z direction. So this is a volume conserving strain. The volume or the density remains the same, but your lattice is strained in a different way. So when you do that, you get a 5.76 Kelvin is the transition temperature. So with a different strain, it may be different. So you may expect a very variable, some differences in the values of the transition temperature. So here it is shown that with strain, the 4%, 5%, 6%, you see the phonon softening at this point and this point. And because of this phonon softening, there is enhanced electron-phonon coupling. So this electron-phonon coupling as a function of strain is shown by this black curve over here. And the estimated TC also shows here. See, beyond this point, it almost non-linearly goes up. So the phonon softening and this biaxial strain, that explains the enhancement of the TC. This is, of course, the density of states at Fermi level that goes into the calculation of this electron-phonon coupling constant. So to conclude, so first we have shown that the high-density non-magnetic phase of cobalt is formed in thin films. And we have actually carried out with a range of thicknesses, 4 nanometer to 25 nanometer. In each case, we got the same picture. Then the density functional theory calculations also show that the high-density phase of cobalt is non-magnetic. And this phase of cobalt shows superconductivity below about 5 Kelvin. And the theoretical calculations have shown the superconductivity of this dense non-magnetic phase of cobalt, and the superconducting TC has been found to increase upon biaxial strain, biaxial volume conserving strain, so its density remains the same.